So we'll start with the contents of week 11 and we'll try to solve some of the questions of week 11. But yeah. Um, yep. Okay. So we'll try to cover those topics which will help you solve the assignments. We'll wait for some time for other people to join. If they don't, we'll just move on and start our session. So is it yeah, start. So today will be like covering these topics that involves topics such as ARP, RARP, bootp, DSCP, and all these things. Um, so so let's say like you are in a you are fitting two computers in a network, like LAN network. And initially, I mean, these two machines do not know anything about uh, your machine, right? So like both party do not know. Yeah, so both the party do not know anything about each other. So before starting the conversation or before starting the communication with each other, you need to first start the um, connection, right? So first you will start with your first you will start with your MAC address, right? So first you start you do address resolution protocol. Okay. So you need a MAC address, right? So first here comes the address resolution protocol. Address resolution protocol helps you find the MAC address given IP address. So the way you get it is uh, you you just say that okay, you just send a ARP request, and in response you get a ARP response. So ARP request is a broadcast request. So let's say this computer in the middle wants to know the IP address, so the MAC address of so it has the IP address of a certain computer, and it has to know the MAC address of that. So it will just broadcast a message saying that I have this IP address. I want to know the corresponding MAC address for this IP address. Please respond me if you have this MAC address. If you have this IP address, so it will just ARP request and ARP request to everyone. So here you'll say, okay, if you have 10.4.10.90, response me, and the same to others. So if you check the IP address of all these systems, the rightmost one has the IP address of 10.4.10.23. So this rightmost system will say, okay, I don't have 10.4.10.90, so I don't need to respond to this ARP request. So I'll say that so it will just stay silent. So this will also stay silent, as well as this as well stay silent. But this system here has the IP address of 10.4.10.90. So since it will see this ARP request, it will respond it with its corresponding MAC address. That is, so every computer knows their MAC address, right? So the goal here is to know the MAC address of other parties in the network. So it will then send its MAC address to the following computer by saying as a ARP response, and it will send that 00.11.22.33.44.55.12. So it will sending with the MAC address to the corresponding system, and this is the way the system will know the MAC address of this corresponding system. Similarly, if anyone wants to know the MAC address of any other system, they will broadcast another message to everyone in the network and ask for the MAC address for the corresponding IP address, and then it will uh, for given the IP address, it will give back the MAC address, right? And after you got the MAC address, you can start communicating. And so ARP is a way of converting the logical address to physical address. So this IP address of a system is called a logical address. Like it's a logic. It's not written somewhere, but the MAC address is written somewhere. Like the MAC address is you know MAC address is engraved into a system or device that you are buying. So it's a way of converting logical address to physical address. Similarly, there is another protocol that works in completely opposite manner, that takes in the physical address and gives a logical address. Like if you have the MAC address of a system, you just broadcast one message saying that I have this physical address or the MAC address of this system, but I don't know the corresponding IP of this. So could anyone please ping me with the IP of this if they have the corresponding MAC address in their device? So if someone has the IP address of that correspond to that MAC address, they will just reply with that. So that is this protocol is called RARP or reverse ARP. So ARP and RARP positions in the TCP/IP protocol suite. So this is the network layer stuff, and this is the IP. On top of IP, there is ICMP and IGMP. On below IP, there is ARP and RARP. So it's a network layer protocol, but it comes in hierarchy a bit below IP. Okay, that means IP header will be there. On top of that, the ARP header will be there, and RARP header will be there. If we read read the formal definition of ARP, it will be ARP associates an IP address with its physical address on a typical physical network such as LAN. Each device on a link is identified by a physical or station address that is usually imprinted on the NIC. So NIC is network interface card. As I said, the the MAC address is imprinted on that, and every device has a unique MAC address. Logical address to physical address translation can be done statistically, not practical or dynamically with ARP. So ARP is a way to convert the logical address to a physical address. Like you give IP saying, okay, I have this IP address. Can you give the corresponding MAC address, and ARP will give you. Okay. Uh, okay, we'll dive into ARP, but before going here, we will let's see the questions first. What is the purpose of ARP cache stability network device? I think we haven't covered it. But which statement is true about reverse ARP? RARP is used to map MAC address to IP address. RARP is relies on unicast. RARP is primarily used in routers. None of the above. So does RARP used to map MAC address to IP address? The answer should be yes, right? Because if you see here, RARP is taking your physical address and giving your logical address. So RARP is used to map MAC address to IP address. That is physical to logical. Yes, that should be true. But I don't know about other options. Once we cover RARP formally in the later part of the course, I mean the later slides, we'll know. Okay. So let's see about the ARP operations a bit. Let me look at this figure first before start talking. Okay. Okay. So this is the same thing as that I said earlier, here they said. Um, so system A and there is system B and there is some other system in the network. So this will say, okay, this will send a ARP request, which is a broadcast. ARP request is a broadcast, as you see here it's written. ARP request is a broadcast. It will send this packet to everyone, like saying looking for physical address of node with IP address this. So I just out of all the system which has the IP address of this, please respond me with the physical address. The ARP reply is a unicast because if these three systems do not have the corresponding IP address, they will not reply. Only the system having the corresponding IP address will reply. Okay. So this system B will reply with the MAC address of that is F4C6E F45983 and so on. The unicast ARP reply is unicast. Then we will see ARP packet. So
Yeah, how ARP header or like how ARP header is designed. First is hardware type. First, you need to specify what is the type of hardware that we are using. So if the hardware type is Ethernet, so it will be type 1 and similarly others. Then the field is protocol type. That is what type of protocol are you using? IPv4 or IPv6. So accordingly, you will use that. Then hardware length, like the length of the hardware, like how many address are there, how many that need to broadcast. Protocol length, length of the IPv4 address. Then operation, like is it a ARP request or ARP reply. Then sender hardware address, um, if I am sending a ARP request, I need to send my MAC address as well, because sometimes a malicious party can send a ARP request and you don't want them to know your MAC, so you have to send your MAC address as well, and they need to verify that it's a legitimate sender. Then sender protocol address, or the sender IP address, target hardware address. uh, the target hardware address is not filled for the request. So since you are making a request, you'll not have this field. You are requesting for target hardware's MAC address, so you'll not have this field. Then target protocol address, the IP address that you have, this IP address you are putting, you're saying, okay, this is the IP address I have. Which system has this IP address? Please send me the MAC address by putting it in this field. Okay, so you just put in this field and send it. So how? So this is a ARP packet, and how do you ARP request or reply packet? How do you go about it? You put it here, then you put type data, and the packet is encapsulated within an Ethernet packet. That means it is ARP request and ARP reply packet are network layer packet, and this is the Ethernet. I mean, this is the MAC header, and this is the physical address header. So there is no network address here. That was the ARP packet and ARP's position in a physical. I mean, this four layer of hierarchy. Yeah. Then let's see four cases using ARP. Okay. So if the first case is like a host has to send a packet to another host on the same network. Okay. So if both the systems are in the same network, and you want to know the IP address, I know the MAC address of the corresponding IP address. So destination address in the same IP datagram. Okay. Then there is case two, a host want to send a packet to another host on another network. It must first deliver to a router. The target so in this case, the target IP address would be IP address of a router. Okay. Then third case is a router receives a packet to be sent to a host on another network. It must first deliver it to the appropriate router. So target IP address is the IP address of the appropriate router found in the routing table. Okay, and the fourth one is a router receives a packet to be sent to a host on the same network. So the target IP address is the destination address in the IP datagram. So this is a fourth scenario when an ARP packet can face. Like in the ARP request, um, the host who has the corresponding IP address might be in the network, or out of the network, or out of middleware, out of nowhere, and or in this case. Let's see an example. A host with IP address of 130.23.43.20 and a physical address of B2 34 50 55 10 22 and 10 has a packet to send to another host with IP address this. Okay. And physical address this, which is unknown to the first host. So this first host has this IP and MAC address, and it knows the destination IP address, but it doesn't know this one. So it will get this as a reply. Okay, the two hosts are on the same Ethernet network, so the ARP request and reply packet encapsulated in the Ethernet frames. Um, okay, so this is the ARP request and reply packet. Now, so you have your CRC, you have your data. In the data, you have your ARP request. Okay, so ARP request data, like you have put your so this all things are other thing, but you can see the target, the this is the your own MAC address, the first line. The second line is the own IP address. This is the MAC address and target IP address. The source MAC address is 123.43.20 and this is 143.25, and this all filled, and source MAC address is given here. But in place of destination MAC address, since I don't know it and I'm sending a request for this address, I'll put these things as zero, all zero. This is the ARP request. So when you put an ARP request, you broadcast it to all the devices. So it's all F now. This is your source address, source MAC address, that is same as this one, and this is your broadcasting address. So but in the ARP is the ARP request. But when you do the ARP reply, the data is now changed. So now the source is this. The source is the one that you are sending from. So now it's a unicast address. Okay, source is this, source MAC is this, source IP is this one 19, because source now this is the source, because this was the source earlier, and so this was the source earlier. So now this is the source, and this is the destination MAC, destination IP, that is same as this first two line. Then this is your preamble, and this is your source MAC and source MAC and destination MAC. So source MAC is now this one, B234 and something. Sorry, this is your source MAC and this is your destination MAC. The source MAC is now this and destination MAC is now this. So this is a ARP reply from B to A, and it's a unicast. That's why you got the proper MAC address of source and destination. But here you got the broadcasted address, right? So this is an example that you should note. Okay, so then we should go to the proxy ARP. So proxy ARP is a proxy ARP running in a router can respond to an ARP request for any of its proteges. The proxy ARP replies with its own MAC address. When the packet arrives, the router delivers it to the appropriate host. Okay, so the proxy ARP is that. So you want to know the MAC address of a system that is here. Okay, so let's say this is the router or host. This one to the ARP proxy ARP router replies to any ARP request received for destination this and this. So this is your let's say you're doing an ARP request and you broadcasted it to everyone. So this system will get the broadcast request, and this router also will also get the ARP request. So once it gets the ARP request, it will once it gets the ARP request, it will start to see that okay, I have these systems and it's a ARP request for these systems. So instead of passing that packet to them and they replying with the MAC address, it will just reply back with its own MAC address and say that okay, you take my MAC address, you forward all the packet that is needed to be forwarded to these guys to me. I will forward it to that I will forward it to them. So that is a way of like way of proxying for the actual ARP. That's why it's called proxy ARP. Proxy ARP, also called the promiscuous ARP or ASP ARP hack, is a technique used to map a single IP network prefix into two or more physical address. Using the same network interface, it is the same network address space for more than one physical address. Assume that there are two networks A and B connected by a router R that runs proxy RP. Using proxy RP, R can use the same net ID for both the networks. That is one uh, advantage. So yeah, so this is the network A, and it's the network address, and this is the network B, this is the network address, and this is the proxy ARP router. I think router are replies to ARP requests that are generated by the host on the PPP connection network P, which in which the target IP address is on the network A, namely sends its MAC address. ARP knows which hosts are connected to through PPP. These hosts assume that the destination hosts are on the same physical network. In their ARP tables, the router MAC address is associated with the destination IP address. Advantage of proxy IP over the networking scheme is simplicity. So it's a way of like saying if you want to know the MAC address of all these people, I'll just sending mine. That's how whatever you want to send, you just send to me. I'll deliver it further. Okay. So this is the thing, and the typical use of proxy ARP. Uh, Taking multiple address family on a normal IP. Okay, so then we are coming to ARP software models. I think the question where from ARP software models. Let's see. So yeah, so since this ARP is so crucial, and where we cannot just request every time this ARP, so that's why we need to maintain some cache, right? We need to maintain some cache or anything that can store this ARP request um, responses and utilize it further when it is needed without querying it again and again. So we can so we are doing this ARP request software module. Okay, so the software module includes cache table, queues, output module, input module, and cache control module. So we'll start with ARP cache table. So if ARP just resolved an IP address, chances are a few moments later there is a request to resolve the same IP address, right? As I said, so there might be multiple requests. When ARP returns a MAC address, it is placed in a cache. When the next request comes for the same IP address, look first in the cache. If there is a IP address, if there is a MAC address present for the corresponding IP address in the cache, then don't go ahead with the request. Just use it, right? If you don't, if you there is not, you make the request, you get a response back. You first save it in the cache, then you use it, so that next time you can just pick it up from the cache. So cache table content, queue number, which queue the ARP request is sitting on, then sitting in, then attempts, how many times have you tried to resolve this address, timeout, how long until this address is tossed out, need the room in cache, hardware address like destination hardware address, destination IP address. So this is the way like you store a cache of IP and MAC pairs. So working of a cache, how does this cache work? There's something called output module that waits for an IP packet with a request. Um, so then the output module will wait for an IP packet with a request. So it sees that okay, it's an IP packet, it's an IP packet, and it is requesting a ARP request. So quickly it will check for the cache for existing entry. If entry found and state resolved, we already have this MAC address. If entry found and state pending, packet wait until destination hard address found. Okay, so uh, this is one of the original cache table that is used for like state is like resolved or pending. So resolved or pending. Queue, then there is attempts, timeout. There is no queue here, and all these things. And protocol address of the IP address of the and then the hardware address of the MAC address. There are a bunch of examples I want to go through, but let me see how. Yeah, let me see how this. A question: the purpose of the ARP cache table networking device to store IP address of all devices in the network, to store MAC address of all devices in the network, to store recently resolved mapping of IP address and MAC addresses, to store routing information for the network. I think I already told this. It will be set with the C, option C, but yeah, you just work it out by yourself. Question number 1 and 2 is done, I think. Okay. We'll go back to the slides and try to. So I think there is none. There is no question on ARP anymore, I guess. Yeah. So you can skip these examples if you want. You can go through these examples and go through lecture if you want to see. But yeah, we'll skip these examples and go to the point where we can discuss about other things that matters for the quiz. Okay. So first and second is done. The next is so next is the next slide set. So it will just a revision. The address resolution protocol. The two messages on a given network can communicate only if they have known each other's physical network address. ARP is solved for mapping from high level IP address to low level MAC address, and this is the picture that we already saw. Next is RARP. So we should discuss this RARP, and yeah, it might be useful for some questions. Let me see. But before starting it, we have 30th slide. I'll take 5 minutes break and then we start after 5 minutes. Sorry, bit of a longer break. We'll start with RARP. So RARP finds the logical address for a machine that only knows its physical address. So let's say we, I mean, I know my MAC address. I need to know the IP address of myself. So this is often encountered on a thin client workstation, no disk when machine is booted, so it need to know its IP address. It only know its MAC address. It need to know its IP address. So RARP requests are broadcasted, and RARP replies are unique, as same like ARP. If a thin client workstation need to know its IP address, it probably also needs to know its subnet mask, router address, DNS address, etc. So we need something more than RARP. So that's why, like, boot P and DSCP, the DSCP is dynamic host configuration protocol, now have replaced RARP. RARP is an old method, it is not using it now. We're not using it now. So RARP operation something work like this. RARP request is broadcasted, like my physical address is this. I am looking for my IP address. If you know it, just tell me. So there's something called RARP server. So RARP server used to respond back with the IP address, and boom, you got it. So this will reply back. And this is RARP packet format. I don't think we need to go through that, but yeah, we can go to the boot P. So boot P is the newer version. Boot P and DSCP is a newer version of RARP. Let me see if there is any questions on boot P. Okay, no, but yeah. So yeah, we will cover it anyway. Bootp stands for Bootstrap Protocol allows a Bootstrap protocol. So it allows a host to configure itself dynamically at boot time. So so it's like, like you have you got a new system and you put it in a you're putting it in a LAN. Okay. So RARP is a way of knowing your own IP address, given that you know your own MAC address. BootP is a way to dynamically configure yourself during the boot time. So this protocol provides three services. One is IP address assignment. Second is detection of IP address of a sovereign machine. Third is the name of file to be loaded and executed by the client machine. And boot packet is assumed to never fragment. Just an extra bit of information. Boot P uses two well-defined port numbers. UDP port number is 67 used for the server, and UDP port number 68 is used for boot P client. The process of boot P, the boot P client broadcasts a single packet called boot request, and the packet contains the client's MAC address. So in the boot request, we know the client's MAC address, and we need to find the server's MAC address through this request. The client wait for a response to the server. If not received within a specified time interval, the client retransmits the request. The server responds with a boot reply packet. Okay. So bootp is an alternative to RARP. Okay, it's not a complete like you can use RARP still. So bootp is an alternative to RARP which operates at data link layer for LAN only. Okay. Bootp UDP IP based configuration protocol provides much more configuration information. Always dynamic configuration of the entire IP address, and bootp and its extensions become the basics for DSCP protocol. So DSCP is the newest. And this is the bootp packet format. I don't see any reason to cover that because it's just packet format. It's just packet format. Yeah, we can see this. Yeah, bootp client is sending a request, and the server is replying it, and client is running on 68 and the server is running on 67. and sorry, 68 and 67, and this is just the way you request and reply in Bootp. Yeah, I think that's it for Bootp. I don't have any questions, I guess, in Bootp, so we'll not go deep on that. Then comes the DSCP. DSCP is the newest one. I mean, the computer that you see in recent days basically use DSCP now. So yeah, you can tell that. So okay. So DSCP is used to centrally allocate and manage TCP/IP configuration of client nodes, and it allows us to define pools of IP address which are then allocated to client computers by the servers. Uh, so uh, so what we do is that so we want to get IP address for a particular thing. So it allows us to define a pool of IP address, which are then allocated to client computers by the server. So we maintain a pool of IP address. Whenever someone requests for a new IP address, we just give one from this pool, and instead of so RARP is, you remember, like, RARP is saying, oh, I have this MAC address, I need my IP address. So can someone give me an IP address so that I can identify myself in the network space uniquely? So so RARP was giving out IP address from RARP server, but this DSCP, what it does is that DSCP maintains a pool of IP address. So it will maintain a pool when someone, even it will get a RAR, when it will get a DSCP request, it will just get, it will just pull one out of that and give it to the target system who is asking for it. Okay. So it allows us to define a pool of IP address, which are then allocated to client computers via server. These pools of different addresses are called scopes. Not only are the addresses being handed out, so also the related configuration setting like sovereign mask and default router, DNS service servers are also handed out to them. Like if you are in a new system joining a network, you will be given out with what is your nearest DNS server, what is your net mask, what is your IP address, and everything. Uh, yeah, DHCP works across most IP routers and allocates addresses depending on subnet the request come from. No need to configure a PC that is moved from one subnet to another. Um when a DHCP client is first switched on, it sends a broadcast packet on the network with a DHCP request. This is picked up by the DHCP server. The server allocates an IP address to the PC from one of the scopes it has. Just if you just recall, scope is the pool of IP address. The DHCP does not allocate address permanently. It leaves the address on a particular time period controlled by an administrator. Okay, so it will just leave some IP address for a, as you can check. So if you go to this website, what is my IP address? You can see your IP address, local IP address. That is a private one. What is my IP? So yeah, it is checking. This is your okay. So this is your IP address. Then if you go to a different network, your IP address will change. Okay, so this is the DSCP packet format, and this is a DSCP operation. You initialize DSCP discover, like then you put DSCP request, then you put like timing as well, like uh, it should keep on a loop, like if if the lease is cancelled, it have to rebind the lease. If the lease time is 50% expired, then it should renew it. And if the release time is 87.75% required, it will rebind an DSC packet and bound it again. I mean, it's like giving an IP address, setting up a timer, and if the timer runs out, the uh, the IP address is gone now. Then you have to request again and get a new IP address. It's like that. So what is lease? So lease means that so if DSCP is operating in a way that, like, I have a pool of IP address, and a new system is joining on. So what I'll do is that I will give one of the IP address to the system, saying that this is your local IP address for now on, till some point, like 5 minutes or 10 minutes, and or like in a couple of hours, a couple of days. So after that point, it will pull back the IP address, and it will the computer has to make another request, and it will get a new set of new IP address out of DSCP server. So since it was just for a temporary time, so that's why we use the term lease. So the IP address is leased to the target computer, and after the lease period is over, it has to lease another IP address again. So this is the typical. I mean, this is exchanging message, like, the between the server and client, and I'll not cover it because it is not needed to go that much deep now. But yeah, so if you want, you can go through the lecture again. So that's the basic idea of DSCP, ARP, RARP, boot P, and DSCP. So these four things we have covered. I think these four things only cover this question number 1 and 2 and 3. But yeah, we'll see what things this LANs and VLANs cover. LANs and VLANs, I think cover 3 or 4 more questions, I guess. Next, let me see what the crack is. Handling loop problem is transparent bridge. It is handled by spanning tree protocol, or STP. Let's see the question here. Question number 3. There is STP here, so you can check that. Let me see if there is question on LAN. Yeah. Okay. So let's start this part. LANs and VLANs. LANs is just local area network, and VLAN is um, virtual local area network. So this is the layer-wise connectivity. So we have application layer, transport layer, network layer, data link layer, and physical layer. And what are the devices that we use in all these layers? Like for transport and application, we use gateway. For network, we use L3 switch or router. For data link layer, we use L2 switch or bridge. And physical layer, we use hub or repeater. So these are like devices which works in this layer, or the maximum layer that they have is this. So if you go to a router and check the layers that it has, it'll have physical layer, data link layer, network layer. But if you go to a bridge, the bridge or L2 switch will have physical layer and data link layer. No network layer will be there. So there's a difference. So routers and okay, this is information. Okay, so routers and hub connect two segment of a LAN or physical address. Bridges connect LANs and connect LAN. So bridge, like, there's a LAN 1 and LAN 2. Bridge is just a, like, like a bridge, like saying is a bridge between these two LAN network. Bridge learning, bridge table, like, when you're creating a bridge between different networks, different LANs. So it creates a bridge table, and in bridge table, you sort of mark like who is in which part of the network. So address A is in port one, address E is in port three, address B is in port one. So let's say want to send something from A to D, so it will come through this and bridge, and the bridge will say, oh, you are going for the D, and D is inside LAN 2, and mm, okay, let's say B. Okay, uh, let's say E. You want to send something to E, so it will say that okay, oh, E is through LAN port 3, so I'll just send this to E, so it will go to E. So bridge is like that. It's a bit dumb device. It's not very um, uh, proactive. So you just send like okay, F and E are in port 3, D and C are in port 2, A and B in port 1. So if a packet comes from A to D, so it will come through this bridge, and it will say okay, it is D, so D means 2, so I'll just send it back by this 2. This creates a loop problem. I'll not discuss it in detail. So it creates a loop problem, and we solve the loop problem using the STP algorithm. So that is what you need to solve this question. STP algorithm, bridge network forward port and block blocking port. Um, okay. So I guess it's not needed. LANs with bridges, virtual LANs. Uh, okay, so virtual LAN is like so let's say, so you buy the idea of LAN, right? Like there will be one wire, and there will be system connected or PCs connected to those ports or hubs. Like you have a computer lab in your university, and you say, okay, this is a lab that we are right now. Like there is computers, is LAN connection is given to every computer. So in the left, you can see there is a typical example of LAN. Like in floor three there is a LAN, in floor two there is a LAN, in floor one there is a LAN. But what happen if some people want to work on the same lab, but same LAN, but they sit in different floors? So here comes the concept of virtual LAN. Virtual LAN, you don't actually physically get connected to the wire. You get connected to the network through like an idea. Like if I am working in building number 7, some other guy is working in building number 5, but we want to share the common network, so we'll create a virtual LAN. And in the virtual LAN, my address will be visible to him, and his address will be visible to me. So it's called a virtual address. And VLANs logically segment switch network based on the function project teams or application of the organization, regardless of physical location or the connection to the network. All workstations and servers used by particular workgroups share the same VLAN, regardless of the physical connection or location. Okay. VLANs are created to provide segmentation services traditionally provided by the physical routers or LAN configuration. VLANs address scalability, security, and network management. Adapters in VLAN topologies provide broadcast filtering, security, and traffic management. Switches may not bridge any traffic between VLANs as at this would violate the integrity of the VLAN broadcast domain. Traffic should only be routed within the VLAN. Let me see what the question was. Okay, so VLAN broadcast driven with VLAN router, VLAN operation, VLAN operation, VLAN operation. Benefits of VLAN. Uh, VLAN types, VLAN types. Uh, oh, there's so much thing about VLANs. And I don't think we can cover all the VLANs. Let me see what topics we can cover in a short duration. Yeah, I think we can, if I pick this, I can cover a bit more than if I just stick in the VLANs. Um, yeah, so I'll cover this wireless LANs instead of virtual LANs. Okay, so let's try to solve this question. So this you can solve it by looking at the slides. Let's go to the question number 5. What is the mandatory access method provided by all implementation of this one? So this is protocol. You can just read through it. Okay, so why do we need wireless local area network? So proliferation of mobile devices like laptops and PDAs created an obvious application level of demand for wireless local area networking, and that's why like IEEE 802 committee started making all these things. So let me see which question also. What is the mandatory access method provided by Volumes? Okay, mandatory access method. Okay, so there is don't tell answers. Um, yeah, the implementation must support DCF, but PCF is optional. That means DCF is mandatory. You're right. Anyway, I'll just briefly tell about the wireless network. So wireless LANs are so there's a base station to wired network, and these computers are connected to by all this through by wireless way of um, communication. So all these station, there is the access point that is also shortly known as the AP, and mm, yeah. So if you want to reach the subway or sorry server or something, this access point. So you reach this access point, and this access point go to this distribution center. So the access point distribution system, and it go to the server and gateway. So this access point you can tell you can think about your mobile towers. So your mobile towers are the access point, and you sort of use these computers to go to this access point. I mean, if your mobile, let's say you're traveling on a road, and your access point change, over time. So, so access point also change. So if you're staying here and your connection bandwidth or connection power to this access point is less than this, so I mean it's more less here and it is more here, so it will just connect to this access point. Stack dealer and physical layer is you don't need that. Wireless physical layer. Let me see. This is done. What is the frame type periodically sent by base station in a PCA based what WLAN? I don't think. I think it will be beacon frame because Yeah, this question. Which IEEE standard specifies a media access controller and physical layer specification for WLAN? I think 802.11, but you need to check this as well. In 802.11.1, what problem does the hidden terminal problem refers to? I didn't cover this. You can check the uh, lectures. Bridges can operate on which of the following two layers? Bridges, which layer? So if you go to bridges part, where we started studying bridges, bridges, uh, one second. Okay. So, uh, one second. You can hear me. Uh-huh. Sorry, I was on mute. I didn't realize. Yeah, I was telling about CSMSCA. I don't know if I. Oh, sorry. Yeah, I was telling about CSMSCA, how it is important for us, and CSMSCA is an alternative for CSMSCD that we use in the wireless. I completely described all these things, but I was on mute. Sorry, but yeah. So I think there is no question in CSMSCA on this topic, so we'll not discuss that much. And we'll close the session for today, and we'll meet you. I'll meet you next week. If you have more doubt in the assignment questions, you can go through the lectures and find out. But I think I have solved 6 to 7 questions, so you'll be fine, I guess. So we'll meet you. We'll meet next week. Thank you.